Hello everyone, my name is Belma and I'm going to present our paper P4QoS, QoS-based packet processing with P4. So networks often concurrently process millions of flows with varying QoS requirements. Hence, deploying per flow specific rules at network nodes would require significant overhead, making such a solution unfeasible. Thus, the goal of this paper was to take a fundamentally different approach, which we call P4QoS, in which we leverage the P4 programmable switches to enable the network to process traffic based on the QoS requirements embedded in the packets. So doing so has two main advantages. First, it enables changeable QoS requirements for a flow on a per packet basis. Basically, if the requirements of the flow would change over time, our solution can handle this. And second, it allows for continuous QoS requirements and not just a set of predefined QoS classes, allowing us to simultaneously support a wide variety of application requirements. So I'm first going to explain the main idea behind this in some more details on a small example. So if you look at network at any time can process many different applications, as I mentioned before. So for example, we can have a tactile app that has a maximum latency requirement of 4 milliseconds, but at the same time we can have a video app that has a maximum latency requirement of 20 milliseconds. And of course, these values don't have to be constant. They can actually change over time depending on, for example, the dynamics or user sections in case of the tactile app. So using P4QoS, when an app starts sending the data, in addition to all the other headers, it appends an additional QoS header that contains the maximum allowed latency a packet can experience. Next, all the routers in the network decrement this value by subtracting the delay components from it. So they subtract the propagation and transmission delay of the output link, as well as the processing and queuing delay the packet experience on the node itself. So finally, when these packets are now received at the second switch, value 4 will become value 3. Moreover, in addition to this, we deployed mechanisms on the switches that try to ensure that packet deadlines are met without any of the flows overpowering each other. However, I'll explain these mechanisms in more details a bit further along in the presentation. So if we go back to our example, when this packet is now received at the third switch, it performs exactly the same actions until the packets are eventually received at the end host. Now, if the second app would start sending the data, it would embed its own maximum latency, so 20 in this second, and the same process will be repeated as for the tactile app. So all the switches would process these packets by taking the maximum latency into account and decrease it so that the value that we have present in the packet always indicates how much latency a packet can still experience until we consider it as outdated. So basically, finally, these packets are also received at the end host. So basically, to implement such a solution that I just presented, we implemented our solution P4QoS consists of two main components. So first of these is the link latency estimation protocol. So if you remember, I mentioned that all the switches actually deduct the propagation and transmission delay. However, switches have independent clocks and their timestamps are only used for locally. Hence, it's not possible to estimate the propagation and transmission delay by simply deducting the timestamps from two different switches. So basically, to overcome this problem and to be able to estimate the propagation and transmission delay, we developed a specific protocol, so link latency estimation protocol, which is the first component of our solution. So I'm going to explain this in a bit more details on a small example. So if we look at a small network with just two switches, and if you're trying now to estimate the link latency between switches S1 and S2, they will be stored in a small register that's present, basically stateful memory that's present on the switch S1. And as we can see here, this value is not known yet because we need to estimate it. So basically now when the application would start sending the data, the first ingress switch S1 will append, in addition to all the other headers, the LLEP header to the data packet and populate it with its own egress timestamp, representing the time the packet left the switch, so T sent in this figure. Eventually, this packet is received at switch 2, and switch 2 now clones the packet and calculates the processing and queuing delay using the its own ingress timestamp, so the timestamp when this packet was received at S2, and the egress timestamp, so basically the timestamp when the cloned packet was sent out of S2, and appends these values to the LLEP header. So now the original packet, so not cloned packet, but the original one, so LLEP header is removed from this packet, and this packet is forwarded to the next switch to be delivered eventually to the end application, while our cloned packet containing the LLEP header is sent back to S1, and we can see now that this header this header now contains both tsend as well as TP plus TQ. So basically the processing and queuing delay on S2. Eventually this packet is received on S1, which uses this information from the packet as well as its own ingress timestamp, so the time when the cloned packet was received, to calculate the link latency between these two switches using this formula, and eventually saves this in its table with the estimated link latencies. So if you look at this formula, we can see that S1 actually subtract the time when basically the time it took from it sending the packet to S2 and receiving the clone, and subtracts from it the processing and queuing it took on S2, and then divides this by 2 because we want the link latency in one direction. What's important to notice though is that we are always using the timestamps from the same switch, avoiding the above mentioned problem with independent clocks and local timestamps. So now that we are able to calculate the link latencies, we can move on to the second component of our solution, which was the cooperative AQM. So this is a queue management mechanism in which the marking target is based on the packet deadline. So the target is actually the value at which the AQM kicks in and starts marking packets. And of course, for our solution to work, we actually do assume that end applications can react to this data. So basically, when the end applications receive the marked packets, that they will react to this by, for example, reducing the sending rate or, for example, the video quality. But they actually can process this data. So basically, our cooperative AQM dynamically adjusts this target value based on the latency specified in the packets and ensures that the flow with the lowest deadline is the one actually determining the queuing delay. So I'm also going to explain this in a small example. So if we have this network with 3 nodes with 2 P4QoS hosts, basically hosts that are exchanging data using P4QoS. So when the first now host starts sending the data, it appends the QoS header, and now the ingress switch, after receiving this header, initializes another field target to the TT here, to the maximum latency specified in the packet, so the value that we had before. Next, it uses this value. From this value, it subtracts the link latency, so latency between switches S1 and S2. And in addition to this, it tries to estimate if this switch is a bottleneck. So it tries to see if there's a queue already present on this switch, eventually calculates these two values, and appends them to the packet, so basically to the QoS header, which now will contain 3 values, so the previous maximum allowed latency, TT, and 0, which is the number of bottlenecks. So eventually this packet is received at S2, which does exactly the same, basically as S1. It subtracts the latency between switches S2 and S3, link latency, from TT, and updates the QoS header. So it also tries to see if it's, of course, the bottleneck, and updates the number of bottleneck header, basically the same way as S1 did. Eventually, this packet is also received at the last switch. So the last switch does some additional actions. So basically, first we need to notice that TT, now, at the last switch, actually represents the maximum latency that can be spent on queuing and processing, so in total on the whole network, because we basically, from the maximum allowed latency, deducted all the link latencies in the network. In addition to this, the number of bottlenecks actually represents the estimated number of bottlenecks that the packet experienced while it was processed in the network. And the third switch uses these two values to calculate the new target. So basically the value when the AQM will kick in and start marking packets, signaling basically to the end host to back off. It eventually also applies this target if it's lower than the currently stored target, making sure that the flow with the lowest deadline determines the target, or if the flow was already determining the target. This way, taking into account the cases when the deadline of the same flow changes and is no longer relevant, so that it can actually overwrite it. In addition, this S3 now forwards the original data to the end application, but also clones the packet and sends this target update that in this case contains both the ID as well as the new target value to S2 and S1. And S2 and S1 now do the same thing as S3, so basically apply it using the same rules. So S2 sends it to S1, and S1 applies the exactly same process in S3 and S2. So okay, like using this, we also implemented multiple versions of P4QoS. So first we implemented multiple versions depending on how we process the packets that violate the deadline. So we have P4QoS that marks each packet violating the target. In addition, we have interval P4QoS, which marks one packet each interval, where that interval is auto-tuned in the same way as codel. So that means that if there was a violation, we reduce the interval. Otherwise, we reset the interval to the default value. In addition to this, we also combined our approach with other state-of-the-art AQMs, such as P4Codel, and tested these combinations as well. So the other thing we looked in is how often we send the update packet, so basically the target update. And here we also implemented multiple versions of P4QoS. So first one was default version, so P4QoS, which sends a target update each time a deadline is violated or a packet of the same flow is received. The second one was fixed P4QoS, which sends a target update only once each fixed interval. And we had adaptive P4QoS, which sends one target update each interval, where that interval was auto-tuned in the same way as codel. So finally, I'm just going to go to the evaluation. We evaluated our solution both in Mininet as well as Tofino switch. And we used two topologies, so a single bottleneck topology and a multiple bottleneck topology. So additional results are available in the paper, and I'm only going to go through the main results here due to the time constraints. So if we first look at the utilization, so we can see that P4QoS, so the green one in this figure, had actually the worst performance at low target values. The reason for this is a very aggressive marking strategy. So basically it marked every packet that violated it. However, in comparison, interval P4QoS had a very good utilization, basically equal to all the other solutions. In addition, we also evaluated fairness. So basically P4QoS again had worst fairness due to the frequent marking, especially at lower target values. In contrast, interval P4QoS didn't have any degradation, but had actually one of the best performances out of all the analyzed solutions. And here priority queuing has the worst performance, because basically the flow with the lower deadline always overpowers all the other the flow with the higher deadline. So fairness was always low. And finally, we evaluated the percentage of packets that violated their deadline. So if you look at no AQM, we can see that almost all packets, due to the formation of queues, actually violate their deadlines. If you look at P4Codel, we can see that if the maximum latency that was specified in the packets was higher than the target, it had very good performance. However, it performed very badly when the maximum latency was lower than the target, because basically the target was static at 5 milliseconds. And finally, P4QoS, it had very good performance, and all packets met their deadlines. And we can see here that only very few packets got marked. And finally, interval P4QoS also had very good performance, very comparable to P4QoS, and basically outperformed all the other solutions. Finally, to conclude, in this paper we presented P4QoS, which is an approach to enable the network to process packets based on their per packet specified QoS in the packet itself. So we showed that interval P4QoS among all the other solutions had the best performance and allowed basically to significantly reduce the network latency in the network while preserving fairness between flows, especially for low latency traffic. And finally, we also combined P4QoS with other existing AQMs and showed that this can actually improve other AQMs as well. Thank you.